Okay, thank you very much. Hello and welcome everybody. And a big thank you to Innovation Martlesham for hosting this session today. Just a really quick background on Chronos's business. Chronos is a subject matter expert company. We've been around for well over 35 years, founded in 1986. We're UK based, we're an employee ownership trust, about 35 people. We are a UK based company, but we have a global footprint. Our business sectors include just about every sector you can imagine. We are a value added reseller and we sell timing systems into most market sectors. In terms of Innovation Martlesham, I have a personal connection. I started my career working for GEC Plessey Telecoms and then Marconi Communications and then Marconi, supporting BT's System X network, and spent many days and nights working on the Martlesham site. And I did notice similarity in the Innovation Martlesham logo to the old Marconi Communications logo with the stylized O in the middle. But as far as I know, Marconi Communications ceased to exist when Marconi formed in the early 2000s, and then Ericsson bought Marconi in 2006. So I don't think anybody's going to be in trouble for copyright. But just highlighting there a personal connection that I have, and of course, Chronos are part of the Innovation Martlesham ecosystem. A big thing in the Marconi days was getting your company logo onto the signs just as you go into the Martlesham site. And of course, Chronos achieved that back in 2020 when we joined the Innovation Martlesham group. There's a photo, very tiny one there, of some of my colleagues standing, looking very awkward, standing in front of the Chronos logo on the display there. So, to the subject of this talk today, time enables everything. We're living in a world really today where all of our personal life and our business life, all of the infrastructure that we use really fundamentally relies on time. Time really does enable everything, whether it's the networks themselves, so the fundamental ways of transporting traffic, the telecom networks, the broadcast networks, they all rely on precise time to be able to function, and the financial services industry as well relies on accurate timestamps to be able to report and to be regulated, to make sure that people don't sell things before they buy them and that sort of thing. And we're seeing now, with the move into big data and AI and cloud infrastructure, lots more information held in databases, whether it's things like in the power industry, voltage and current measurements, or whether it's all the applications and the cloud software applications that we use. And these are global databases, and they need to be synchronized globally. And UTC, Universal Coordinated Time, is the global timescale that's used generally to do that, and it's GNSS clocks, so Global Navigation Satellite Systems. That's the generic acronym that describes all the satellite navigation systems like GPS, Galileo, GLONASS, and Beidou. And we've really sort of become dependent and reliant on those clocks to synchronize most of our everyday transactions and life that we lead. And it's typically increased bandwidth demand and performance demand on these comms networks that means they have to use the resources they have a lot more efficiently, which requires better time alignment handling. And of course, the more and more sensors we have, whether it's just state of charge of your EV as it's charging, and that's feeding back data into the power grid so that the power grid can be balanced, or whether it's any sort of data sensor that's reporting data into a network, it requires accurate time handling. And a really good case in point for why that is important is some of the LTE advanced technologies within 4G and also 5G. They both use time division duplex TDD systems where they're sharing the radio resource, and they have each user equipment, each handheld mobile phone has an effective time slot in which it's allowed to transmit, and all those time slots from all those phones, when they arrive at the base station, they all have to be in the right place to minimize interference. And even commercial things like the Raspberry Pi, the small credit card sized computer, now has PTP support in it. So even those off-the-shelf cheap computing resources have accurate time capabilities. So the next few slides are going to quickly look at 5G and why it needs accurate time. A couple of things going on in the mobile space at the moment. So with the 5G, this so-called functional decomposition, and where you used to have a mobile base station that would be in a cabinet, it would be in a physical enclosure next to a mast that would hold a passive antenna. So you'd have a passive antenna with some passive coax going down to the cabinet. All the electronics and the software would be located within that enclosure. But in 5G, there's functions that create that base station function have been disaggregated. They've been decomposed and split across the network. So now we have, to the right of this slide, we have the actual radio unit that is effectively a software-defined radio. We then have front haul, which would be some sort of fiber connection going back to a distributed unit, which may be physically located with the radio head or may not, maybe further afield. And then towards the left-hand side of the slide, we have the mid-haul taking those functions back into the centralized unit. So now some of the non-time critical function, the management functions can be performed in maybe cloud infrastructure. But you see how the base station function has been split into these sections, and Open RAN, ORAN, the Open Radio Access Network, is opening up these interfaces between those functions and publishing and opening the specifications so that different manufacturers can build those different components. So we don't have to buy all our equipment from vendor A or vendor B or vendor C. We can have different manufacturers supplying different parts. And in terms of synchronization, these are some of the high-level 5G synchronization requirements. Around about a microsecond and a half from the core to the edge of the network. And then between adjacent radio units in 5G, we have this either 130 or 260 in category A or category B, or 3 microseconds in category C, time alignment handling. So now very strict time alignment handling requirements at the edge of the network. And in terms of the clocks and synchronization, what that can look like is all of those parts, the radio unit, the distributed unit, the centralized unit, are all connected by fiber. Typically that's running radio over Ethernet. So they're typically Ethernet-based services. And we're running the clocks, the synchronization to meet those stringent requirements for 5G is running either synchronous Ethernet or PTP. And we have GNSS-based clocks as the reference clocks for that. So you can see how that technology that gives us the massive bandwidth and the spectral efficiency in terms of numbers of bits per hertz that 5G achieves is by utilizing these very well controlled, very well time aligned radio resources. So again, a very high level look at why time is important in those sorts of networks. And I mentioned on one of the previous slides, IEC 61850. So this is an IEC standard to do with digital substations. So this is specifically focusing on the power industry. And it talks about a digital substation, this idea of a digital substation. Now, these are protection and control monitoring equipment that looks at the power distribution resources and works out if it thinks there's a fault or some sort of error in the system, and is able to then turn bits of the power network on or off to accommodate that. Typically, it was lots of different technologies at the physical layer that they used to get time synchronization in there. But this 61850 standardizes on Ethernet, an Ethernet network, again, using PTP, the Precision Time Protocol, for time synchronization. Typically using HSR or PRP redundancy, so you'd have a dual redundant Ethernet network. And this idea of the digital substation, again, sometimes called a timing island. So it doesn't necessarily matter exactly what all the clocks are traceable to, as long as in this sort of timing island, they're all traceable to the same clock. But usually that is a GNSS-based clock, and we would have some sort of dual redundancy. But I'll come back to this slide later in the presentation after we look at some of the clock architectures that are used and being deployed within the networks to support this. In terms of overall requirements and networks, how they've progressed, we've got right the way back to some of the original requirements in the UK. This is post office requirements from 1976, specifying an atomic clock that can make that has a frequency error better than 1 part in 10 to the 11, and this is the typical cesium beam atomic clock accuracy that is used. And as I say, this is still in some of the networks, still written into some of the ITU standards today, but this predates the CCITT, which is what the ITU was before it was the ITU, and these are from UK post office requirements. And it's interesting how things have gone full circle. So back in those days, we had circuit switch networks, and we're now talking on packet networks. This is a diagram taken from a Cisco white paper where they're talking about the CSSR, which is circuit style segment routing. So this is a technique using Ethernet packet networks and using fixed paths across the network to emulate these private lines. It's like the old PWE, private wire emulation. They're calling it private line emulation, PLE. But it's interesting how we've moved away from circuit switch networks to packet networks, and then now on packet networks to still service some of those applications at the edge of the network. We're using those circuit switched ideas, but overlaying them on top of packet networks. And the significant thing in terms of synchronization here is at the bottom of the slide in the middle. This talks about using a frequency reference, just like those post office requirements from 1976 talked about using atomic clocks as a frequency reference for those PDH and SDH networks. We're now using a similar idea, but using synchronous Ethernet or PTP, the precision time protocol, or at the bottom of this slide, it says BITS, BITS, which is a North American acronym, Building Integrated Timing Source. So a BITS clock is what we would typically call an SSU or a SASE style clock from the European SDH regs, but it's basically the same thing, a frequency reference for the network. So even though the networks have changed over the years to supply, to work in different ways, the way the fundamental networking technology works, we're still servicing those applications at the edge of the network that may be 4G or 5G base stations that require frequency stability. We're using similar ideas and similar philosophies from those original circuit switched networks. It's interesting to look as well how the reference clocks that have been specified within the ITU. So the ITU is the International Telecommunications Union. That's a global body that's actually part of the United Nations. It's a global standardization body. And this G811 in the middle column of this table, G.811, is the original primary reference clock standard that goes all the way back. As I said, it predates CCITT. Excuse me. And that was in place, and it was the primary reference clock standard for a good few decades until packet networks and applications that connect to the packet networks, the telecom applications and other industries as well, like broadcast and finance and the power industry, realized that they needed time synchronization to be able to support the applications that they were using at the edge of the network. So in 2012, the first of the sort of time standard, so moving away from purely frequency references to adding a time aspect, was the PRT specification that came around in 2012. Then very quickly that was enhanced to ePRTC. They just snuck a small lowercase e in the front of the acronym. So PRTC is primary reference time clock. E is the enhanced version. The original G.811 was updated in 2017 to an ePRC that again had a 1 order of magnitude better frequency accuracy, parts in 10 to the 12. And then now the latest one that was released in January of this year is the coherent network primary reference time clock, which I'll get onto later as to how that fits into the hierarchy and what that actually looks like. So initially these primary reference clocks were frequency only, and they were based on the commercially available technology at the time, cesium atomic clocks that would give you a part in 10 to the 12 or better of frequency accuracy. So the standard was written an order of magnitude lower than that. And then, as I say later, time and phase traceable, again, time traceable to UTC. So that implies using a GNSS or other source of UTC to within a certain error threshold of UTC. So initially, the initial PRTC specification was 100 nanoseconds of error to UTC. ePRTC then gives us better than 30 nanoseconds of error. And interestingly, the way of building that clock, that particular design of that clock, included using GNSS and atomic clocks together. And the idea was the atomic clock is very accurate. It has a very small frequency error, but it's fixed, it's linear. And if we can effectively measure that or work out what that frequency offset is by comparing it to GNSS over 21 days, for example, 3 weeks, then we could, in a holdover scenario, when if GPS or GNSS is interfered with, if there's some jamming or spoofing or some problem with an antenna, if the signal goes away, then we can enter what these clock systems call holdover, where they lose their reference and they just run on their own internal clock. If we can gauge what that small frequency error in the cesium clock is, then we can apply a correction factor should we lose GNSS. And the original specification for the ePRTC was better than 100 nanoseconds error to UTC for over 2 weeks. And it's just been updated. The ITU study group is just looking at updating that to 40 days or more. So we'll give you, in the event of a GPS or Galileo outage for up to tens of days, 40 or 50 days, you can maintain better than 100 nanoseconds of error. And the latest standard that was released in January is this coherent network, which is a network of this style of clock meshed together. And again, there's a slide later on that describes exactly how that looks. In fact, here it is, the next slide. So it's a network of these coherent network, a network of ePRTC clocks that provides this coherent network in a similar style to the way the national metrology labs are all effectively connected together and all contribute their clocks into the BIPM in Paris to realize UTC. These clocks have local GNSS references, local atomic clock references, but they also have network feeds from other clocks similar to this. So again, it's a way of a network operator, maybe a large network operator like BT, like France Telecom or Deutsche Telekom, building a network to give them resilience within their own networked layer, the terrestrial network layer, and remove dependence from GNSS, because we know that those signals are fragile and can be interfered with. But it enables us to build architectures like this. And this is a very high-level example of providing that sort of architecture where the network, the clock lives in the network, and we can get very small errors of to UTC. Even if the GNSS signals go away for weeks and weeks, we can still supply that signal to, for example, our 5G network. So this slide has some 5G base stations down the bottom where we're being able to meet those accuracy requirements that 5G has of the microsecond and a half from core to the edge, or 130 or 260 nanoseconds relative error at the very edge of the network using this sort of architecture. And this is obviously a very telecom focused example. Going back to the power industry and going back to the earlier slide, this is our digital substation, but now rather than just treating this as maybe a timing island on its own, lots of energy companies, utility companies are looking at, again, much more efficient ways of working if they do have a common time base across the whole network. So not only is it the requirement that the substation, the timing island, has to be synchronized to a clock, the whole network is synchronized to a clock, and that happens to be UTC. And so they can make very accurate measurements of the way the network is behaving and performing on maybe a regional or even a national level. We're using the same time base across a whole national network. So all we've changed on this slide is I've just added at the very left this idea of the vPRTC. So this acronym with the V at the start, the V is the virtual primary reference clock. So the network effectively becomes the primary reference time clock because it has these EPRTCs embedded within it. So anywhere where we can get accurate optical direct fiber access to our network, we can get access to a clock that is in within a few nanoseconds of UTC, and in the event of a system-wide outage or holdover event, then it would maintain less than 100 nanoseconds to UTC for weeks and weeks. And this is obviously the idea focused on the power industry, the digital substation, the idea of using a common time base. And this could be a telecom network on the left that's providing, again, maybe the precision time protocol and synchronous Ethernet for frequency, using a telecom profile. The time servers within the digital substation, or in the center, there is the HPBC, the high performance boundary clock, could then be translating that telecom profile of PTP into the power industry profile to then serve time in the event of GNSS outage to the whole substation or to the whole network. In terms of non-terrestrial networks, that's an interesting development recently. 3GPP has introduced support for non-terrestrial networks, so that means satellite and maybe airborne platforms. They've specified frequency division duplex only so far, so that's significant in terms of time. I'll come back to that again. And they're talking about serving handheld devices, so the typical smartphone application, or narrowband IoT, or this MTC type of, similar to IoT type of communication to sort of IoT devices. Two different architectures they've suggested. There's this so-called transparent architecture, which is sometimes known as a bent pipe, because effectively we are just taking the 5G signal, the 5G radio signal from the ground, and we're then using a satellite to take it up to space and rebroadcast that radio signal. So the payload is the same effectively, and the G node B, which is the 5G base station, that function is still on the ground, and the signal, effectively the 5G signal to the base station, terminates on the ground. So that's the first transparent architecture. The second is the so-called regenerative architecture, where some of the base station functions are now on the space vehicle itself, on the actual satellite. So again, you get a much more efficient use of the radio resource from the satellite, and you get a much smaller round trip time. But that means you have to have this functionality. You have to have more intelligence in the space vehicle itself. And obviously, launching a satellite is, a significant cost, as an economic cost to it. So it has pros and cons. Here's a table, a really high-level summary of geostationary, that's GEO, medium Earth orbit, MEO, or low Earth orbit, LEO satellites, and also HAPS, this HAPS, high-altitude platforms, which could be drones, or they could be airborne, they could be aeroplane, sort of helicopters, or what we traditionally think of as airborne vehicles, helicopters or things that look like aeroplanes, or they could be drones at a much lower level. And there's a little table here just summarizing the altitude, the round trip time in milliseconds, and the beam width that's available. I think the next slide is really just a text summary of that diagram, so I'll skip over that quickly. In terms of synchronization for NTNs, non-terrestrial networks, the platforms themselves could use GNSS signals. Obviously, they're away from any sources of interference that might be on the ground, so they can sometimes they can get much better or less error-prone reception, being either on these airborne platforms or in space vehicles further up in space. And 3GPP has only specified frequency division duplex. So the reason why the TDD systems need this well-defined time alignment is because of this guard period between the transmit and receive switch. So they're using the same frequency to transmit and receive on, and there obviously has to be a period of time when the transmitter's not transmitting and the receiver's not receiving, the so-called guard period. But because of in some cases up to hundreds of milliseconds of round trip time up to these high satellites. Such a guard period would be very, very long relatively and result in very inefficient spectrum use. So for that reason, there's no specific time requirements on synchronization for NTNs, although there are obviously frequency accuracy issues there, but the satellites and the platforms themselves can lock onto signals from the ground station, so they can effectively frequency lock to their uplink signal, which can keep them within specification. Interestingly, low Earth orbit, OneWeb is talking about changing their signal, being able to use for PNT, position, navigation, and time. They've got 2 generations, an early one where they're using some techniques to use existing hardware in space and existing signals, and then generation 2 after 2028, where they've got a different payload on the satellite. This is a slide that I took from a presentation by by Terry Sullivan, who at the ITSF conference last year in Antwerp, where obviously, again, a different application. They're looking at low Earth orbit satellites here for backhaul to get connectivity to remote sites. But Terry actually did some tests where he ran PTP, the Precision Time Protocol, over that backhaul service. So it obviously wasn't optimized to do that, but it's just interesting that the non-terrestrial networks have their applications outside of actually delivering signal to remote handsets. They're actually used as of the infrastructure. So in terms of these time systems, it's always good to consider the security and the resilience of them. Chronos has long been involved in work on looking at interference to GPS. GPS jammers are around for lots of privacy reasons. People don't want to be tracked in their vehicles, right up to organized crime gangs who want to disable all tracking and communication for high value assets they might be stealing. But not just jamming, spoofing as well. We can build signal simulators out of things like, again, the Raspberry Pi and a software defined radio for a few £100. There are YouTube videos out there. You just type in GPS signal simulator and Raspberry Pi and software defined radio, and you can get step-by-step instructions. The little slide that just appeared at the top there, 0 to operational in 10 minutes, is from a presentation by Logan Scott, a very well-respected expert on GPS, where there's a YouTube video telling you exactly how to do it. So we obviously have to consider the security, and one of the reasons why we're moving to these architectures where atomic clocks are embedded into the network is because we're becoming more and more aware of the fragility of these GNSS signals, and not just from jamming and interference on the ground, but also space-based attacks as well, whether it's lasers directly attacking satellites, or old decommissioned satellites being steered into the path of working satellites. There's a lot of concern about geopolitical different nations attacking other nations' space-based assets. And this slide, resilient time as an attack vector, is really interesting. It's a group of security researchers based in the Netherlands, Midnight Blue, who reverse engineered the encryption in Tetra. So Tetra is trunked emergency services radio that the police, fire, ambulance all use. And the encryption in there was a closed encryption algorithm. It's specified by ETSI. It's an ETSI, European Telecommunication Standards Institute, an ETSI standard. But these researchers managed to reverse engineer the encryption by using unauthenticated time signals on the network. They were able to force the radio and the base station to drop down their level of encryption to the basic level, which we're then able to brute force attack and engineer. So it was interesting how again, time as an attack vector, always be wary that any time signal that you're using on the network could be attacked. In terms of what we can do to get around that, the mitigations, I've talked a little bit about the ITU clock architectures, building resilience into the network, antenna positioning and installation. Obviously, autonomy is about zero trust, not trusting time signals, having your own time scale. SOOP, the SOOP acronym is signals of opportunity, maybe using other signals for time, whether it's low Earth orbit satellites, maybe some terrestrial radio or ELA-RAN backup. And again, keep in mind that's a cybersecurity mindset based on, any time signal can be spoofed. So bring some autonomy in-house, build clocks that have atomic clocks built into them, be careful of accepting time from outside sources, test and monitor permanently. And again, from cybersecurity, these ideas of zero trust, authenticating everything and secure by design, building networks, building services and applications right from the start to be absolutely 100% as secure as possible. And so to the summary, really, this is the penultimate slide in the deck. These new clock specifications allow us to build networks which can be resilient, which can hold resilient time sources, such that if our GNSS signals were interfered with, they can give us better than hundreds of nanoseconds of error to UTC for many weeks. Any location, any site you have, whether it's in the core of the network or whether it's to the aggregation layer or the edge of the network, wherever you can get network access, you can then effectively have your own primary reference time clock supplied by those clocks that you've built into the network. And obviously you can use that as a primary source if you want. I've got your own time in italics here is just, it could be a corporate timescale, it could be a regional timescale, it could be a national timescale if you want to create your own, a different national timescale for your own network. But whatever that timescale is, it could be the primary source or it could be used as a backup if there's any interference to those GNSS signals.